Welcome to The Explainer. Pretty much every piece of modern software you touch, your phone, your apps, the websites you visit, it's all built on one really powerful concept. Today, we're going to dig into that idea, object-oriented programming.
All right, to really get this, we got to go back in time a bit. Imagine you're programming in the old days, using a language like C. You want to keep track of an employee's info, right? So you'd bundle it all up in something called a struct. Think of it like a digital index card. You've got a spot for their name, their ID, their salary, all neat and tidy. Looks good, right? But here's the thing. This simple little box has a huge, huge flaw. And this is the problem. Right here. See that line of code? What it means is that any part of your program, literally anywhere, can just reach in and mess with that data. So you could have a totally unrelated bug, maybe hundreds of lines of code away, that accidentally sets an employee's salary to 0. And poof, it just happens. There's no wall, no security guard, nothing to stop it. The data is just out there in the open, totally vulnerable.
Okay, so this leads to a really big question, a problem that developers were wrestling with for a long time. As our software gets more and more complex, we're talking millions of lines of code, how on earth do we protect our data from this kind of chaos? How do we build things that are safe, reliable, and don't just fall apart because of one tiny mistake?
Well, the answer wasn't just a patch or a quick fix. It was a total game changer, a whole new way of thinking about how to structure code. And this big idea was given a name by the brilliant computer scientist Alan Kay, object-oriented programming. And seriously, this wasn't just about new syntax. It was a fundamental shift in how developers approached building, well, everything.
So what's at the core of this whole new approach? It's this thing called a class. Now, don't just think of it as a better struct. It's more like a master blueprint for an entire machine. It doesn't just list the parts, that's the data. It also includes these specific tools and instructions, the functions, that are allowed to work on those parts. It's all bundled together, locked inside one secure package.
Okay, so how does this actually come to life? Well, this whole philosophy is held up by what are famously known as the 4 major pillars of OOP. Think of them as the essential rules of the game. A programming language has to support all 4 of these to really be called object-oriented. Let's walk through them one by one. First up, we've got abstraction. And honestly, this is all about making things simple. My favorite way to think about it is driving a car, right? You just use a steering wheel and a couple of pedals. You don't need to know anything about the engine or the transmission to get where you're going. Abstraction is the exact same idea for code. It hides all the crazy complicated stuff on the inside and just gives you a simple set of controls to use.
Okay, pillar number 2, encapsulation. And this is the direct solution to that problem we talked about at the start. Encapsulation is literally the act of building a protective shell, or a capsule, around your data. It locks the data and the functions that can touch that data together in one unit. So the rest of the program can't just barge in anymore. It has to go through the official front door.
And look at this, it's the perfect side-by-side. On the left, you've got the old way. That salary is just out there. Anyone can grab it. But on the right, inside the class, we've marked the salary as private. It's hidden. If you try to change it directly from the outside, bam, you get an error. The only way to modify it is by calling that public setSalary function, which gives us complete control.
All right, pillar number 3 is modularity. And this is all about organization. Imagine you're building a giant spaceship. You wouldn't try to build the whole thing in one giant piece, would you? No way! You'd build the engine, the navigation system, the life support, all as separate modules. That's modularity. You break your big program into smaller, independent, manageable pieces. And that brings us to our 4th and final pillar, hierarchy. This one is super clever, and it's all about not repeating yourself. Code reusability. So you can set up relationships. For instance, a manager is a kind of employee, right? So instead of starting from scratch, the manager class can inherit everything from the employee class, and then you just add the extra stuff that only managers have. It's just so efficient.
Okay, so we've been talking about the class as a blueprint, and that's exactly what it is. A blueprint for a house isn't a house, right? You can't live in it. To get a real house, you have to build it. In programming, that building process is called instantiation. It's how you create a real usable object from the class blueprint. And you know what's crazy? In a language like C++, this is all it takes. That one little line of code. Employee E1. That's it. That's the command that tells the computer, hey, go grab that employee blueprint and make me a brand new working copy of it. Call it E1. And just like that, an object is born. We have an instance that's ready to go.
So we've got our object. It's alive. Now what? How do we make it do something? Well, remember encapsulation? We can't just reach in and fiddle with its guts anymore. Instead, we have to communicate with it properly. We send it a message.
And this is what that looks like. When we write e1.acceptRecord, we're sending a message to the object. It's like politely asking, hey, E1, could you please run your acceptRecord procedure for me? We trust the object to handle its own business. It's this clean, controlled way of communicating that makes the whole system work so well.
So let's bring it all home. What's the big deal? Why does all this matter? Well, it all comes down to this. Object-oriented programming gives us the tools to fight back against complexity. We get simpler code thanks to abstraction. We get safer data because of encapsulation. We can manage massive projects with modularity, and we save a ton of time with reusability. It's the toolkit that lets us build the massive software we rely on today.
And I want to be super clear here. This isn't some dusty academic theory. This is the architectural foundation of your digital life. The operating system you're using right now, your web browser, that app you were just scrolling through, the systems that run our banks, our hospitals, our power grids, they are all built on these exact principles. It's what allows them to be so incredibly powerful and yet somehow remain stable and reliable.
So think about that journey. We went from just simple, raw data to these smart, self-contained objects that could model concepts from the real world. It was a massive leap that totally reshaped how we built software. Which, of course, leaves us with a huge question to chew on. What's the next big idea? What's that next paradigm shift that's going to once again completely change how we build our world?